Hello, am I
Hi.
audible? Am I audible?
Hi, Sai. Hello.
Am I audible?
Yeah, yeah. Yes, you are audible.
Okay, so let's just wait for 5 minutes, maybe if anyone else join.
Sure, sure.
Till anyone joins, you can introduce yourself. I'm seeing you first time in this session.
Okay. I am Pavaman. Actually, I used to attend Unlock IC design course, one
Okay,
with Mayank. He's from IIT Kanpur.
okay,
So,
okay.
yeah. So that happens on Sunday.
Mm-hmm.
So earlier to this, I used to attend from Nishant AB. He's from IIT Madras.
Okay,
Uh, so he also used to do analog electronic circuit, same circuit design course.
okay.
And
I think these are two different courses, right? I think Mayank was doing NOC 19. Uh,
analog IC design, yes,
this is analog circuits. It's a
circuits,
undergraduate level course, right?
yes, yes.
Okay, okay.
So so I just wanted to get a basic overview. I'm into
Okay,
systems.
okay,
Just
okay.
just wanted to check if
There is something of the
oh,
interest.
yeah, yeah. Not to check, but not always we are right. So
Okay, okay, fine. We actually in these sessions we do you must be knowing, right? We do the questions and solutions.
basically, yes. So
Hmm.
it's more into circuit designs and BJTs and FETs, right?
BJT,
So
yeah, MOSFETs.
MOSFETs, FETs. So sometimes some linearizing technique, biasing technique is what I think it
No,
would be.
actually,
Mhm.
maybe I don't think in these many weeks that has been discussed.
Okay.
So this will be actually biasing techniques and everything like voltage divider, you have current mirror and those many things. I don't think
Okay.
those have been taught yet in this course, and I don't know
Okay.
is that in the content of the course or not.
Mm-hmm.
So
Okay.
these are simple BJT, as much basic as you can go.
Oh, okay. Okay.
Okay, yeah, yeah.
Okay. Then maybe. Okay. Fine. I was
That's
basically going into.
that's why I said the course which Mayank was doing was I think different than this one.
Yeah, Mayank is doing unlock IC design course.
This is a
It's
simple, and let me just show one question,
yeah.
kind of questions like this.
Oh, okay. Okay. Got it. Okay. Understood.
Oh, yes, yes.
So it goes into basically saturation or linear region, and we find the V out.
Yeah, yeah.
Yeah, I got it. Okay. So, what the earlier classes I used to attend was one from electronic circuits where we had this solving the complex two-stage op-amp amplifiers.
Okay, okay.
Uh,
Maybe that will be in last week's. I have not gone through content properly, but
mm,
maybe that will be in last week's. But that still will be undergraduate level, and
oh,
this is
okay.
a UG course. So,
Yeah, nevertheless, no issues. Thanks, Sajid, but
yeah,
it was
yeah.
nice interacting with you.
So you are doing PhD, right? Or
No, I'm into what is that? Is I am into unlock devices.
okay,
Right? So I'm working with them.
okay,
So
okay, okay,
we are currently doing some in-amp design,
okay,
instrumentation
okay,
amplifier.
okay,
So
okay.
I was into the IC design. I thought this course is, since Nishan doesn't join, I thought you would be continuing with that
Mm,
lecturing. So he does
no,
often on the Friday evening.
no. This is actually different. Actually, I have a session on Tuesdays. I was in IIT Madras in last Tuesday, so I postponed my session. This is, I think, you have opted for wrong, wrong one because
Oh,
this is not that course. I think that you have.
oh, okay, okay,
Yeah,
okay.
yeah, yeah. Actually, I have postponed my session. My sessions is usually on Tuesdays.
Ah, okay, okay, okay,
Okay,
okay.
okay. That's, I think, it has went wrong.
Oh, okay, okay. I'm
Yes,
not
yes.
sure then.
Yeah, yeah.
Mm, Session 2 is on 7 p.m. to 9 p.m. Ah, okay. There are two sessions actually.
Yeah,
Today,
actually, this is a that will be a completely different course.
yes, yes, yes.
That's why
I'm
when you said this is a design that I thought, I think you have mistaken something.
yeah, yeah, yeah.
Okay.
Nevertheless, Sajid,
Yeah, yeah.
nice
It was
talking to
nice,
you.
nice.
Yeah,
Yeah, it was nice
yeah,
talking to you.
yeah, sure.
Okay, okay.
Sajid, you are from which part of India? Like basically from
Mm,
Kerala?
no. I'm from Kashmir.
Kashmir? Oh my God. Good man. Good to see. Nice,
Okay,
nice. Yeah.
okay,
Thank you. Thank you, sir.
okay. Yeah, thanks.
I'll drop off.
Yeah. You have course
Hmm.
on 7. I will just wait for 2 3
Seven.
minutes. Maybe if someone will join, then I can
Okay.
start.
Great, 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 great.
Okay.
Okay. Thanks.
Thanks, man. Okay, so I don't think anyone will join. Maybe they have attended previous session on Monday. So let's just start solving these questions. You can always watch this video on YouTube, right? So before we go to solving this question, and let's just recall some things from previous week. Okay, the second. We should know that what is beta. This is IC by IB. What is alpha? That is IC by IE. This is always greater than 1. This is always less than 1. This should be remembered. Okay, so now the question says for the circuit shown in this figure, VB is given, VC SAT is given, beta is given to us. Beta is given to us. Okay, thermal equivalent voltage, as you know, this is KT by Q. This is 26 millivolt. This is at room temperature. Remember that T is in kelvins. Temperature is in Kelvin. K is Boltzmann constant. Q is charge. So at room temperature, the value is 26 millivolt. Okay, now early voltage is given as very high. That means VA is very high. So what does that mean? We have studied in this last session. What is early voltage for a BJT? If you have characteristics like this is ICVCE. Early voltages when you extrapolate these curves on voltage axis. right? This is your early voltage. When VA is high, that means your device goes accurately in saturation. So there is no increase in current after you approach a saturation voltage, right? So in this question, you have now IB is given to you as 12 microampere, beta is 150. How do you have to calculate? Find the output DC voltage. We have to find this voltage. Okay, so what do we have in hand? KVL, KCL. So here we have to find this voltage. What will be the best rule we should follow? If I go in this direction, KVL, right? So it will be 12 volt here, then current flows through here, that is IC current, and there will be drop in this resistor, okay, and this will be output voltage. So basically this will be 12 minus IC times resistor value is 3.3K, right, minus VCE cube equivalent to 0, right? Now VCEQ will be equivalent to 12 minus IC 3.3K. Now we know beta is given to us as 150, which is equal to IC by IB, right? So this is IC. IB is given to us as 12 microampere. That will give us IC as 150 into 12 to 10 to the power minus 6. Calculate it. You will achieve an IC of 1.8 milliampere, right? So now you have this equation. Substitute value of IC in. First we get VCEQ is equal to 12 minus 1.8 milli, that is 10 to the power minus 3 into 3.3 into 10 to the power 3. When you solve this, you will get a VCEQ of 6.06 volt. Now there is one option of 6.06 volt. So why we didn't use this loop? If let's say it would have been right, let's say if it was like this, then maybe we would have been able to use one KVL through this loop as well. But here this node and this node is disconnected and we are doing DC analysis, so we can directly use this loop independently, right? Okay, so just remember that from questions 1 to 4 we have common values of beta, VBE, VTS, okay, and IB 12 microamp. Okay, now next question is calculating the transconductance of GM, the BGT, sorry. We know conductance, again just for the repetition, conductance is inverse of resistance given by I by V, and transconductance will be transmits, it will be a transferred conductance, right? From this output to input. Output to input. Output I out, input V in. So transconductance is I output by V in, denoted by GM. Okay, so we have to find transconductance of the amplifier which is given to us, and then find the amplitude of the signal current flowing through the collector terminal. Okay, now given to us is Vn of 6.5 millivolt. Remember that this is this V here. Whenever actually we calculate, whenever it is mentioned that you have to calculate amplitude or something, you talk about AC at that time, right? So V in is calculated here, given to us as 6.5 volt, which in actually will be some signal A times, let's say, sine of omega t. This amplitude is given to us as 6.5 millivolt. That is a max amplitude, V peak voltage. Okay, so this is a peak voltage that is given to us, and with corresponding to this peak voltage, we have to calculate our amplitude of the signal current, that is I out, that is I C. For that, we have Gm is equal to IC by V in. Now, what we have to calculate is Gm, right? So, let's say we go by definition of collector current, we can write collector current as IC is equal to Is exponential of VBE by VT, right? So if I differentiate this DIC by dVBE, here IC is output, input. So it will be Is exponential of VBE by VT 1 by VT. This will give me IC by VT. This implies GM can be defined as IC by VT, right? Now IC, as calculated earlier, what was the value of IC? 1.8 milliampere. And what is the value of VT? 26 millivolt. So both, 1 second. So IC is given to us as 1.8 milliampere and VT is 26 millivolts. So our GM will be equivalent to 1.8 milliampere divided by 26 millivolt. Milli goes. This will be 1.8 by 26 ampere per volt is the unit. So this is our GM. Let's keep it at that way. Now our aim is to calculate amplitude of the signal current flowing through the collector terminal. Now again, going by definition of GM, this is I output by V in. This will give me I output as V in multiplied by GM. V in is given to me 6.5 milli to GM is 1.8 by 26. Let me just calculate it. 6.5, 1.8 divided by 26. This comes out to be 0.45 milli. That means our output is equivalent to 450 micro ampere. So 450, yes. So this is one option which is closed hours, which actually is a exact value. Okay, so this is how you calculate GM or BJT, and you derived this formula by using this expression. Sorry, actually I had to trace back. It takes time. Okay, next question. What does the question say? Question says you have to calculate R pi. What is R pi? R pi is the internal resistance BJT from base to emitter. We will draw equivalent circuit in last slides, then we will see why does R pi fit in. Okay, for time being, just say that R pi is, if you go by Ohm's law, R pi will be VB or Vin by IB or I. This is a, we can say that input resistance of BJT, right? Okay, so now we can define R pi as, if let's say R pi is VBE by IB. If I multiply it IC by IC, multiply and divide by IC by IC, you know beta is IC by IB. So my R pi will be equivalent to VBE by IC, okay, into beta. What does this give me? Remember GM? What is GM? GM is I out by V in. So can we write GM in place of this? Right? So this will give me R pi is equal to beta by GM, right? Now from the previous question you have, you know GM, you calculated GM, right? This is our GM, and what else we need is beta. Beta is given to us 150. So my R pi will be equivalent to beta by GM, that is R pi will be equal to 150 divided by, what was GM? 1.826. Calculate it, let's say, and let me use the calculator. 150 into 26 divided by 1.8, that is 2166.66, that is 2.166 kilo ohm. So let's see, is there any option? Yes, right here. This one is the closest option. So you just What you've learned in this slide is that you can calculate your R pi by using formula. You can directly use this one. Can use R pi. This is the important formula. You should remember this. R pi is equal to beta by GM, and your GM is 1 by M, which is already calculated. So what we take from these slides is your GM for VGT is hmm, IC by VT, number 1. Your R pi is beta by GM, number 2. Okay, and we derived this from this relation. Okay, so this is done. And last part I think in this question is, now we have to again find output signal. Let me just copy the circuit. Let's see. I'm not able to copy a circuit. Let me just draw it here. It will take me less time to draw. Okay, this is 12 microampere. Okay, so the question says find the value of output voltage signal. Output signal voltage, V output. We have to find V output for V in of 3.25 millivolt. Okay, I can show you this solution using equivalent circuit, and but that will be discussed later. You can just directly note down that your gain, that is V output by V in, can be written as GM into R, right? GM is your transconductance, R is your resistance at the output, that is here 3.3 kilo ohm, right? Okay, so we know, let's just calculate for this. Sorry, 1 second. One. Share screen again. Hmm, it is visible. Okay, so now we have GM we calculated earlier, that is 1.8 by 26, that we know. And we know the definition of GM, that is, if this is I out, we know GM will be equivalent to I output by V in, right? We will get to this formula as well. So we know GM, we know V in. V in is given to us 3.25. Now can we calculate I out, right? So I output will be equivalent to GM V in, right? Then I output will be equivalent to 1.8 by 26 into 3.25 milli. This will give me I output. What value comes out to be? Let's just calculate it. 1.8 into 3.25 divided by 26 point. That comes out to be 225 microampere, right? Hmm. Now we have to calculate V out. That will be simply given by I output into 3.3 kilo ohm. That will be equivalent to 225 into 10 raised power minus 6 into 3.3 into 10 raised power 3. Let's just calculate 3.3. It comes out to be 0.749 volt. Is there any option closest to this one? Yes, there is one option. So this one is the current we used it. Right here. Okay. So can we just now go to this formula? Ultimately, we use this formula, right? We used here V output as I output into R, right? If I see here, V output is equivalent to GM R into V in. If I use this as I output into R is equal to GM R V in, R goes, I output is GM V in, right? We use this formula, so we can write V output as V output by V in as gain that is given by GMR. This R can be written only when there is no intrinsic resistance. If there will be intrinsic resistance, R will come in parallel to that. So we will see this later. So this was the question, part 4 of this question. Let's just move to question number 2. And for 5th and 6th part, you have these common values. 0.6, beta again given to us as 200. Thermal voltage is 26 millivolt. And here, but early voltage is given here. Early voltage is given to us as 100. Okay. VBB is such that the DC current through the base terminal is 10 microampere. So VBB is not given to us, but it says that it is such that the base current is 10 microampere right here shown. Just look at the circuit. Use the effect of R naught for analysis. We have to use the effect of R naught as I said in this slide. R naught. Let's just see. We have actually discussed R naught as well. R naught is given as VA by IC. This is for channel length. We call it as channel length modulation in MOSFETs. So here also this is the early effect, that is how much current will increase with applied collector voltage. So just to let you know what is the significance of this resistance. So what we have to calculate is V output by VB, this point, not this point. So for this question, we have to draw an equivalent circuit. Equivalent circuit we know the equivalent circuit, right? Second, we have studied about equivalent circuit in our first session also. Like for example, for diode, for diode, we drew diode as a resistor and a battery of some voltage, right? Similarly, we can have equivalent circuit for BJT, for MOSFETs as well. So here, for this circuit, for this circuit, let's just draw the equivalent circuit. So what you do in drawing the equivalent circuit, you note down three nodes. It's a three terminal device. So this is a three terminal device. You note down three nodes. One will be base, collector, and emitter, right? Then you see the circuit, then you just draw these elements. Here we see that there is a resistor attached to base of 2.6 kilo ohm, right? Emitter is attached to ground. You know that this is an equivalent circuit and this is small signal equivalent circuit or AC equivalent circuit. So DC biases grounded, right? So we have here V in, this voltage, VB will be grounded, and 3 kilo ohm will be connected to ground as well at V output. This is our V output. This will be resistor 3 kilo ohm, and we have R naught here as well. And further we have gain of the circuit, that is GM times this is VB, GM times VB. Okay, this is it. And here, like I said, this is a R pi. Here the resistance of R pi. This is your equivalent circuit for BJT. Right now, what does the question say? You have to find V output by VB. You have to find this V output by VB. So what is the first step you will do? First step is obviously drawing the equivalent circuit. If you drew the equivalent circuit correctly, you can do this question easily. Now look at the figure. See, where can you use, no, let's say, will you use KVL here or you will use KCL here? Which one is the easiest here? Okay, just note that in these equivalent circuit questions, most of the times what we do is we use KCL at this node. Alright, so if you use KCL at this node, let's say hypothetical current is not hypothetical, I output current comes in this way. This will go in three directions, right? And these have two nodes, common nodes, so these two are in parallel. So what I can write is that V output by R naught plus V output by 3.3 kilo ohm plus GMVB is equivalent to 0. There was nothing connected to emitter, right? So emitter is grounded. So this is my KCL at this node, let's call A node. KCL at node A. Fine. So I can write it as V output R naught 3.3K R naught plus 3.3K is equal to minus GM VB, right? Okay. And now let's just see what VB is. We drew the circuit. This is GM. This is 2.6K. This is your R pi, and this is your ground. This is your VB. So we have to calculate VB in terms of first. No, the question first said was okay. So here we have to calculate V output by VB. And this can be directly calculated, right? So here V output by VB. Well, this is okay. We can do this later. Just ignore this for a second. Now let me just erase it. Let me just erase it. We have to calculate with respect to VB, not V in. Okay, so V output by VB, V output by VB will be equivalent to minus GM into R naught into 3.3K divided by R naught plus 3.3K. Hello. Okay, let's just continue. So we know what is given to us. Okay. Mhm. We have circuit. Okay. Okay, we have given to us everything. Now we need to calculate GM, right? From the definition we saw here. Okay. GM is IC by VT. GM is IC by VT. GM is IC by VT. IC will be equivalent to beta is given. Beta is given to us as one second. Let's open this question. Okay. Data is given to us as 200. So IC by IB is equal to 200. IC will be equal to 200 into IB. And IB is given to us as 10 microampere, right? Yes. So my GM will be equivalent to IC, that is 200 into 10 into 10 to the power minus 6 divided by 26 millivolt. This will give me GM as calculated, it will be 1 by 13 Siemens. Right, so now you know GM. Now next step is calculating R0. Okay, so next step is calculating R0. What was the definition for R0? It is simply VA divided by IC, right? So in this question, what was the VA? VA is given to us as 100 volt. Okay, and IC, this is 200 into IB. IB is 10 microampere, right? Okay, so you get R0 equivalent to 1 divided by 2 into 10 to the power minus 5, right? Okay, now you know R0 as well as GM. Now what we have to calculate is V output by VB, right? We have to just substitute these values. So V output by VB will be equivalent to, let me just write this formula again. GM was calculated as 1 by 13 into R0 as 50K 3.3K, and go is calculated into 13, 12.69 divided by, here's K, would get the output by VB equivalent to minus times 69 divided by 50. Let's see options first. Okay, okay, I forgot to give the options. Wait a second, just check. Point 5, 200 It's near about 218. We got slightly higher value. Okay, now it's just maybe it's a calculation mistake. So this is how you will do this. This is your equivalent circuit. This is how you do KCL at this node. You have to just write V output at KCL at this node. You will get a V output in terms of VB, and you will proceed as it is. Okay. Now in this question, what is given to us is V input is given as 11 millivolt. Find the value of output voltage signal. We have to find V output. So again, let's just draw again the circuit. V input. In this question, what we have to do is that you have to find V output in terms of V in. In previous question, we had to find V output in terms of VB, right? Okay, so VB, can we write VB as simply R pi divided by, okay, what is the value of this resistor? 2.6K, 2.6K, 2.6K into Vn. Vn is given to us. Now we only need to find R pi. R pi, we did, we calculated the formula for R pi, we derived it. R pi can be simply calculated as Vt by Ib, right? Vt is given to us as 0.26, that is 26 millivolt, and Ib is given to us as 10 microampere. Let's just, sorry, this is 0.026, 26 millivolt. This comes out to be 2.6 kilo ohm. So my R pi is also equivalent to 2.6 kilo ohm, right? Now you have VB, therefore your VB will be equal to 2.6 kilo ohm divided by 2.6 kilo ohm plus 2.6 kilo ohm to V in, that is V in divided by 2. Now V in is given as 11 millivolt. So V output again at this node, V output by, you follow these steps, V output by R here at this node, KCL plus GM by VB, GM VB equivalent to 0. What you will get is that on substituting VB in terms of V in, you will get V output as GM R parallel R naught multiply V in. Now GM, we also have calculated GM. We have calculated GM, we have calculated R naught. We have calculated GM as, let me just check, 1 by 13. We have calculated R naught as 50K and R is given to us as, 1 second. or is given to us as 3 kilo. Okay, so V output is equivalent to 1 by 30 into 50k parallel 3k, and V in is V in should be equivalent. This should be V in by 2 because actually it is a VB, so there will be V in by 2. Got this value. It's 11 millivolt divided by 2. Solve this, you will get V output equivalent to around 1.2 volt. This option. Okay. So this was a follow-up question for the previous one. Now moving on to this is a question on MOSFET. So a little bit of introduction about MOSFETs. Two types, PMOS, NMOS, right? What is the difference? PMOS has current carrying carriers are holes, and in NMOS the electrons. So basic structure of MOSFET is, if I draw a basic schematic of MOSFET, source, drain, this is NMOS, let's say, this is your gate, so we call this as a substrate. If this is a NMOS, so channel has to be of electrons, so your substrate should be of p type, call it as p well, all p substrate. And the source, drain are n-doped. We have studied about doping in first session, right? So you know doping. So these are n-doped materials. This is a p-doped material. Gate, we have here oxide. And then we have metal, or we have usually polysilicon as well. So what is the principle of MOSFET? What happens in MOSFET? We have three regions of operation. Okay, number one, accumulation. Number two, depletion. And number three, inversion. So most of the times you operate your MOSFET here because when you want to get most of the current from the device, your device should be in inversion. So what is accumulation? As I said, for NMOS, channel should be of electrons. But if you now see here, this is your simple MOSFET structure, this is a P well, and if you apply gate voltage, which is negative, right? Accumulation means getting piled up, same carriers as that of your substrate. So what happens is, if you apply negative voltage, it will attract more holes in this region. So holes will get piled up, right? So that is called as accumulation. This happens in when Vg is negative. Next, you start increasing your Vg voltage. You start increasing your Vg voltage. What will happen is accumulation charge will start dropping off, and slightly the electrons will start coming to this region. Since P-well is Na, it has Na carriers, NAR have holes, right? So there will be some atoms which are less of electrons, one less electron, which have one less electron than silicon. They will catch some electrons and give a charge of Na negative at this region. Still, in this region as well, your device is not that much conducting. This is called as a depletion. Happens at when Vg is increased towards positive value. So we get a Na negative values. Then inversion. What is inversion? When further Vg is increased further positive, more and more electrons will pile up at interface. This oxide P-well interface. And we call inversion by definition. What is the definition of inversion? Is that when concentration of electrons at interface is equal or greater than the majority carriers. Here for NMOS, majority carriers are holes, right? P substrate. So this is inversion. So if I draw, let's say, IDVG characteristics, which is like that only. So if I say that this is my threshold voltage, that is when inversion starts appearing, inversion occurs. So this is my, let's say, depletion region, and this is in negative side, you have accumulation region. So these are three regions of operation of MOSFET. Okay, so that was on the basics part. Let's see what does the question say. Okay, so you have this circuit. The value of device parameters is given, and for let me write the simple model for current calculations in MOSFET. IDS is equivalent to mu n Cox W by L VGS minus VTH VDS minus VDS square by 2. This is for NMOS. For PMOS, IST, we just change the polarity, rest is same. Remember that this is always to be positive. In saturation, however, what is the saturation condition in MOSFETs? we say that if I draw IDVD, let me just draw a single curve. We say that this is the value of VD after V saturation occurs. So we define saturation voltage at VD sat as a voltage when VGS VD sat is when, one second, we define VD sat as that value of VDS when VDS is equivalent to VGS minus VTH, right? So at that time, IDS can be written as mu Cox W by L VGS minus VTH. This is again VGS minus VTH minus VGS minus VTH square by 2. So your IDS will be equivalent to mu Cox W by 2L, because this is square 1 VGS minus VTH whole square. This is for a case when device is in saturation, and in most of the questions you will see that we will use this equation. Okay, so now going back to the question, what does it say? Your KWL, remember that KWL is written for this term. Your K is given as mu Cox. So your KWL is given to us as 0.5 milliampere per voltage square. Okay, your threshold voltage is given to us as minus 1 volt. Since it's a PMOS, so your threshold voltage will be negative. These two values are given to us, so what we have to calculate is we have to calculate the operating point. That is, this is your source, this is your drain, so we have to calculate VSD, call it as a quiescent point, and we have to calculate ISDQ. So in a nutshell, we have to calculate first the current that will be given by this formula, right? So we have two options. Either we use for this formula, number one, and either we use number two. Let's start with first one. Let's see what difficulties we will face. Since it's a PMO, so we'll write ISD is equal to K W by L, which is VSG minus VTH, VSD minus VSD square by 2, right? If you just go back to this figure, this is VG, right? This is your source. If you just use a voltage divider here, what you will get? You will get VG equivalent to 20K divided by 20K plus 20K multiplied by 8. That comes out to be 8 by 2, that's 4 volt. So your VG is simply 4 volt, right? If your VG is 4 volt, and now what will be VSG? That is Vs minus Vg, and Vs is given as 8, so that means 8 minus 4 is equal to 4 volt. So Vsg is 4 volt. This is given to us. And what about VSD? VSD. Can we write VSD as 8 volt minus V output? Right? This is simply V out. So my ISD will be equivalent to K W by L 4 minus 1 V, that is 8 volt minus V output minus 8 minus V output square by 2, right? But if you see from the circuit again, V output will be equivalent to the current of ISD flows here. So the output will be simply called ISD into 2K, right? That is ISD into 2K. So it will become ISD equivalent to KW by L 3 8 minus ISD 2K minus ISD 2K square by 2. So now if you go on solving this question, this can be solved, but it will be a quadratic form, right? You have ISD square here, simple linear term ISD linear term ISD. So this is one way you can go on solving this question by following this approach. This is solvable, right? Now more easier, and as I said, in most of the questions it's assumed that the device is in saturation. We can directly use formula ISD as KWL by W by L2 into VSG minus VTH square. Let's just write the values, that is milli, 0.5 milli by 2, VSG we calculated as 3 minus 1 square, that will be equivalent to 4 into 0.5 into 10 raised power minus 3 by 2, right? Okay, sorry, this is VSG was 4 volt, so this has to be 9 here. That comes out to be 2.25 milliampere. So this is your ISD, or we can say that this is your quiescent current. Okay, now what about VDSQ? That will be simply equal to VDD minus V output, that is 8 minus ISD into, what was the resistance value? 2 kilo. That is 8 minus 2.25 into 2K. Solve this, you will get VDSQ 3.5. Options please. VDSQ is 3.5 volt and this is the D option, right? So this is how you solve this question. Okay, moving on. Now we have to calculate a small signal voltage gain for the same circuit. Let's again draw small signal circuit. Alright, let me first draw main circuit here. Without DC supplies. Just look at 2020. Okay, 20K. Okay, this is grounded for small signal analysis, right? There was nothing in series. Now there is a 10K resistor in series. 10K. We have to find V output by V in. Okay, this is a PMOS, right? So now just simply this is your V in. This will be 20K parallel 20K. is GM VII. This will be your 2K, and this will be your V out. Where we will apply KCL? Obviously here, right? So it will become V output by 2K plus GM VII is equal to 0. That is, your V output will be equivalent to minus GM times 2K to VII. And your VII is equivalent to, this is 20K plus 20K, that is 10K. This is also 10K. So your VII will be equal to 10K divided by V input, right? So VII will be equal to V input by 2. So your V output will be equal to GM. Now you have to find GM as well, right? Now as you know, IST is equal to KWL by 2, W by L to 2, VGS minus VTH square. So GM is simply DIST by dVGS. So your GM will be by definition equivalent to by 2L, right? VGS minus VTH. For PMOS, this is for NMOS. For PMOS, it will be simply equal to by 2L VSG minus VTH. This is mod VTH, right? L here, sorry. So we know the values. This is by 2, this is 4 minus 1. GM comes out to be 1.5 milli. Now we output. Mod of V output will be simply equal to 1.5 milli into 2K to V input by 2. This will give me V output by V input. It's equivalent to 2 and 2 will go 1.5. This is the gain of the circuit. So we are done. The part is the right answer. Okay. Now, I think it's the last question in this MOSFET part. Find the input resistance seen by the input signal source for the cell. So we have, let's say, this is our MOSFET. What is seen? What does seen mean? You can see resistance from here. You can see resistance from here. You can see resistance from here. One moment. 1 second, please. Okay, so you can see resistance. What's happening? You can see resistance from, let's say, this is your drain, this is your source, this is your gate. If you say resistance from there, this will be output resistance, and this will be input resistance, and this will be source side. It can be source can be act as output as well as input, so let's just call it as source resistance. How do you calculate it, and what is the way to actually um, calculate the resistance value? What we do is that if, for example, this is my resistor, I don't know its resistor value. This is my single strand resistor. What I will do is that I will come up with a voltage supply, which I know the voltage, and I connect it to it. And I know I have emitter as well. What I will do is that I know voltage and now I have emitter as well. What will happen? I don't know R value. So I give the voltage, I know the current. You go by Ohm's law, that is R. Now you know Vx, you know Ix, you can definitely find Vx, you can definitely find R. So this is the approach that is also used in these devices as well. By going through the question, what does it say that you have to calculate input resistance? So my circuit, equivalent circuit is like this, 10k, 10k. We should not bother about these values because we are only focusing on V input. So this is my Vx, and let's say current Ix flows. So that will be equivalent to Vx will be equivalent to Ix times 10k plus 10k, right? And we know resistance is Vx by Ix. So here Vx by Ix is 20k. So my input resistance is simply equivalent to 20 kilo. If I have to find output resistance as well, I will just apply a series voltage here and here X, and this has to be shorted at that time. So let's just do this. Let's just do it. You have ground here, 10k, 10k, VI, GM, VII, so that you can do other questions as well if something pops up. This is your Vx. So since this is grounded, VI will be 0. This will be open because no current flows. So my circuit will become as this will cut off because this is grounded. It has no worry regarding this related to this. So this will simply be grounded. This will be open. This is R. This is Ix. This is Vx. Now Vx will be simply equal to R times Ix. So output resistance is simply equal to R. That is 2 kilo ohm. So just to show you that how you can find resistances. Now if you apply a Vx at emitter side, you can now calculate it. Just do it yourself and let me know what is the value of our source side. Sorry. Okay, this is done. Now last to 10 to 12. What does the question say? For the circuit shown in figure 3.4, consider the value. 1 second. Okay, now it's fine. For the circuit shown in figure 3.4, consider the value of device parameters. This value was given to us. These values are given to us. early voltage, which is important to note down. Okay. Now we have to find operating point. Now we know what operating point is. Just for the just for the case to let you know, whenever you apply, whenever you use transistor as an amplifier, right? You have to bias the transistor, right? And on top of that, you apply AC signal, and then you check performance like gain, amplitude, waveforms, and phase, right? This kind of things. So basic operating point for the amplifier is DC operating conditions. What is the DC voltage? What is the DC input voltage? What is the DC output voltage? These kind of things are called as operating points. So here we have to find VCEQ and ICEQ. Okay, so this is my circuit. This is one loop, right? This is another loop. What is the current that flows in this resistor? Here, no, DC current will be IB. DC won't flow through here, right? So this is IB, this is IB, and this is IC. So if I apply a nodal analysis here, so the current total will be here in this resistor, IC plus IB, and here this is IE. Okay, so now since I had to find these values and I had to find VCEQ, that is this voltage, VCEQ, what I will do is that I apply KVL to get these values. Let's apply the KVL in this loop, one loop, and this is second loop. 1 kilo ohm resistor, this is 12 minus total current of IC plus IB flows through it, 1 kilo ohm as I said, minus 97k IB, and also we have given is zero point 0.6 volt here from his VBE is given to us as 0.6 volt, minus 0.6 volt. Again, this is minus IE times 1 kilo ohm. Total sums up to 0. That's what KVL says, right? And we know IE is equivalent to IC plus IB. And from beta, definition of beta, this is IB. So I can write IB as IC by beta, right? So let's just substitute these values. We can write it as minus IC plus IC by beta 1k minus 97k IB, replace IB by IC by beta, minus 0.6 volt minus IE is IC plus IB. Let's just write it 1k equal to 0. Okay, so this will be 11.4 volt minus this is 1 times, this is 2 times IC, 1 plus 1 by beta, beta is 99, 97k IC by, okay, here it should be beta 99 is equal to 0. This comes up to be 11.4 is equivalent to 2 times IC 100 by 99 plus 97k, sorry, this is 2k here, by 99 IC. So this is equivalent to 11.4 is equivalent to 200k plus 97k by 99 IC. So IC will be equal to 11.4 into 99 divided by 297k ampere. Let's just calculate it. 11.4 into 99 divided by 297 comes out to be 3.8 by 1000. That is your IC. This is your ICEQ. This is a Q condition. Okay. So what was asked? Let's say solve the MCQs. One of the trick is to see the options, right? We got ICQ as 3.8 milliampere. Now, if you look at the options, only in option A there is 3.8 milliampere. If you have done calculations correctly and you are staying in exams that are competitive exams, one of the good way to solve the question is to go through options. Now, if you have found ICEQ, now if you have done it correctly, you can just directly write A as the answer, right? You don't have to find VCEQ. But for the sake of knowing things, you should, and since it's a subjective work currently you're doing, so you have to find VCEQ as well. Just as a trick to solve MCQ questions in competitive exams, like you may be sitting in next couple of years or something. Now to find VCEQ, if I go through now loop 2, if I go through now loop 2, what I can write is this is 12 minus IC plus IB, 12 minus IC plus IB 1K minus VCEQ minus 1K C plus IB. Have I done it right? Yes, 12 minus 1K C plus IB, then VCEQ, then IC plus IB 1K. So this will be 12 minus 2K times IC plus IB. IC is 3.8. Let me just first write IC divided by IB is IC by beta is equal to VCEQ. This will give me VCEQ equivalent to 12 minus 2K into 3.8 milli 100 by 99. Let's just solve that quickly. That is 7.6 into 100 divided by 99. That is 12 minus 7.6767. Just subtract it from 12, we get 4.32. That is 4.32. Like I said, now you go through the option again, that is 4.32. Now, out of this is good, right? You can always use it. Moving to the next part. Again, we have to find our pi, that is internal resistance from base to emitter. You know, our pi is I usually forget this formula. Let me just check. Either I have to go back slightly, just write it quickly here. DIC by dVBE. This is helpful for you too. You can always go back to the root of the equation that comes up to be, so that you don't have to remember everything. So this is 1 by R pi IC by Vt. So your R pi is Vt by IC. So you know R pi will be equivalent to Vt, that is 26 millivolt, and your IC is 3.8 milliampere. Hmm, one moment. Okay, think something is wrong here. Divided by 3. Let me just check. Okay. Oh, sorry. Okay, I have done this mistake. And this is a output current, and I have write from base to emitter. So what I have to write is, I have to write IB here as I naught exponential of, let's say it's VB by VT. Then I can find this R pi as VT by IB. Let me just first go to how we define this relation. And this, okay, or not. Here. Okay, one way to define it was beta by GM. Okay, let's pick up from this point, beta by GM. Beta by GM. Okay, R pi. R pi is equal to beta by GM. And by GM, you know, GM is VT by IC. Right? So you can write R pi is equal to VT by IC. I think I have again mistaken here. I see. Yes, I have made one more mistake here. This is IC by beta. IC by VT, sorry. Couple of mistakes here. Should never be worried about mistakes. Mistakes are good for learning. So this is IC by VT, right? And now you know beta is IC by IB. So your I R pi will be equivalent to replace beta by IC by IB, you will get IB. This is how we will get relation for R pi in terms of IB. Now just let me erase this part. Okay, I will do that later. So we got it R pi as R pi is given as Vt by Ib. So your this is 26 millivolt divided by Ib is what's the value of Ib? Ib is given to us. No, Ib is not given to us. Okay, IC is given to us as 3.8. We calculated IB. So IB will be equal to beta will be equal to IC by IB. So IB will be simply equal to IC by beta, right? So your R pi will be equivalent to 26 millivolt into beta, that is 99, divided by IC, that is 3.8 milli. So your R pi will be equal to, let me just calculate it, 26 to 99 divided by 3.8, 677.36 ohm. Let's see the option 677, right, this one. Okay, so just if you happen to see this, please do note that this is a wrong relation in terms of if you want to find R pi. Okay, now moving on. Last question. Find the intrinsic gain GM R naught. Intrinsic gain GM R naught. Okay, so you have to for that you have to find GM and you have to find R naught. GM is given as IC by VT. Fine. This will be 3.8 milliampere divided by Vt, that is 26 millivolt. So this is 3.8 by 26. Let's keep it as it is. And again, your R naught is Va by Ic. Va is given to us as, okay, let's check. Va is given as 100. 100 and your Ic is 3.8 milli. So your 100 divided by, let's keep it as it is. That is 100 into 10 is power 3 by 3.8. So your intrinsic gain GMR naught is simply equivalent to 3.8 by 26 into 10 is power 5 by 3.8. This will go, so 800 by 26 kilo, that will be equal to 100 divided by 26, that is 3.84 kilo gain. Gain is unitless. Why it is unitless? Because it will be V output by V input. This has voltage unit, this is also voltage unit. So is there any option? 3.84, yes, this one, right? This will be 3.846 K. So this was about transistors. Again, questions regarding related to BJT and MOSFET. Again, if you happen to watch this video, if you have any questions, you can always ask in phone or in comments. I will correct that slide as well. Okay, this one, right? Okay, I will do that later. So let's just end this session.